Last but not least, to deploy network coding, it's not so important anymore to convince manufacturers to put it into their standard or to put it into their hardware. With the new area of communication networks where computing kicks in, where softwareization is there, then you will hear in ComNet 3 about software-defined networking, network function virtualization. And this means the door is open for us to bring these ideas into the networks. Because we can now develop an encoder, take it as an NFV component and put it in the network. We can place a recoder and put it into the network. We can even change the placement of this recoder on runtime depending on the loss rate and the dynamics in the network. I think Zuo has some very good examples for that, where you can test it out on your laptop with Mininet and Docker and so on. Okay, just to explain you a little bit, I think these examples, maybe you've seen it in ComNet 1 already, just to explain you what happens in a multi-hop scenario when you use store and forward, right? You have a sender and a receiver and some stupid repeater in the middle. And here you generate enough redundancy. G is the amount of data that you normally have, you want to convey to the other side. And alpha is the extra redundancy. And the extra redundancy you have to generate at the first node is the redundancy that keeps you alive until the end, right? And here you see that the first link has to carry most of the load, and here you kill the whole thing because you put too much traffic on the link. It's not so much on the last one, that's not the problem. And theoretically you can now can calculate the number of packets that you will need. It has to do with the initial number of packets G, with the number of hops H, and just the erasure. Here I assume the erasure is the same. Otherwise, you make here a different symbol, right? And not just to the power of H, then you have to make a product out of each of the links. But you can also calculate the delay. How long will it take until you have all the packets, right? Down here. I will not go into detail. If you now make an end-to-end code, so here you start to code, sorry, this was end-to-end code. If you now make a hop-by-hop code, right? So if you just say, to avoid this amount here, I will just send everything to the first one. Once I have it, I will decode and then send the rest, and then I will decode on this side, encode again, and send it to the other side. Then you have a hop-by-hop one. Then you look, oh, now the number of packets has decreased significantly. The delay depends on the epsilon, right? And the other parameters that is here, of course. But you already see, okay, less packets, but maybe I need more time for that. And the other thing, and I'm sorry, but this is not totally correct, but what you will do is you send packets, and whenever you have something, you recode and send it to the other side. And here, of course, you cannot send anything because we did not receive anything. The pattern is a little bit unlucky, right? But you understand when you have network coding and recoding, here you can start to create the recoding. Now, if you look at this, the number of packets will be the same, right? You see it also in the equation. That is not what gets better. It will only be better in the delay. So that we have done in a virtualized concept. It's called Escape from the University of Budapest, where we said, okay, let's take a virtualized one. Zuo has his own simulator for that. And we say, what is end-to-end or uncoded versus our RLNC approach with recoding in the middle, right? And there's a way how you can put this together. If you have end-to-end, you just need an encoder here and a decoder here. The rest is a forwarder. Here you need to make a full encode decode, and here the recoder. And then you look what are the number of packets over the losses, and you see end-to-end goes up, while hop-by-hop and RLNC are more or less the same. And they're exactly the same, okay? And this one is theoretically, and the other one is measurement. So for the number of packets, this theory and the other one holds perfectly. Now what is with the latency? Here you see the latency over the number of hops over the losses. This is end-to-end, and you see it goes up if the losses go up and the number of hops go up. Remember the first link, you fill it up with a lot of redundancy. And it goes up to the, here's, you see the hundreds of seconds. If you do hop by hop, you don't also go up, but it's only 10 seconds here, right? It's very low compared to the other one. And network coding is even better. I think we have a plot by the gain, I hope. Yeah, this is the gain. This is the first one is end-to-end versus RLNC, how much better RLNC is versus end-to-end, and how much better RLNC is against the hop by hop. Interesting is that hop by hop we are beating when the losses are small. End-to-end we are beating if the losses are high. In other words, we are beating them. Now the question is, SDN, how far are we? In Aalborg, we had our first SDN testbed with 16 PCs, with FPGA cards and one switch over here. We tested it out. And why did we have FPGA cards? We had to be fast. At that time, we were not fast enough on the software side, so we had our graphic cards to help us a little bit. And there's one paper where we all summarized all the stuff together with Jonas and Daniel, Jeppe, Muriel is also there, where we said, let's do the following. We have this virtual machine where the coder is there. We have a virtual interface and a virtual switch on the host. And when the uncoded flows comes in, we just get it out. If the coded flow comes in, we have to give it to the virtual interface, do something here, and virtual out. This problem is a little bit complicated, and it causes a little bit of latency, but it was the first implementation that was there. Now, I'm coming back to this topologies again, right? If you now have point-to-point, there's a real SDN testbed, right? We have uncoded TCP versus end-to-end and versus end-to-end coded TCP, right? And then you see here, this is the theoretical capacity of your link. It's only 1 minus loss probability by the rate. Then this is TCP. TCP goes down as soon as it sees errors, right? Because it cannot distinguish congestion with errors. And then you have the coded version here. And the coded version has still, there's something to the optimal, but TCP has it, but sometimes 3 times higher than the TCP one, right? So it proves what we said before, right? And this is real traffic on that. Now, if you have now a recoder in the middle and see how we did it, we have an encoder, we send it out, the recoder, we give it to the PC, do all the recoding and bring it back. So we are losing a lot of time in doing that. Nevertheless, if you look at the gain here, there's a 7x gain in switching the coding on, and even a gain with the recoder. The same for multipass, and here you see 4x, 2.5x, very complicated because we have so many streams here. Therefore, here you have the encoder, the decoder, there are 3 passes with 10 milliseconds and 0%, 10 milliseconds and 2%, and here is something in between the recoder, so very complicated. In order to understand it, this is the uncoded one, very bad. These are the end-to-end coding, so when you do encoder, decoder, and you just forward on the end, this is here, and the better ones are up here. So back again, if you see, if you do a lot of redundancy on your link, because it was not adaptive, then you're losing a little bit. The weaker one gets more. Why? Of course, part of the capacity is not used by your redundancy. As soon as the loss rate kicks in and you don't have enough redundancy, it goes down, while the other one stays stable and goes down a little bit later. The same over here. Depending on the ratio, on the redundancy level, you have something here where you can gain, but then if it's too weak, you're falling down. And this one is stable over time and then also goes down in the end. But the gains are there, and this is something that we have now proved. This was an older implementation. Now here you see a robot with Ericsson. So now it's nicely integrated in the flight rack, in the 5G flight rack, where you can show now with recoding, without recoding, and get the whole thing. And we don't have this extra delay with this setup that we had in the beginning using the FPGA cards that help us to be fast, but also cost us time just to get them started, right? Okay, with that, I would like to finish the lecture of the use cases. I hope that you understand that there is already some space where the technology takes place. And it's very important also to see that there are some places where network coding shines alone, others where it is as good as the others, or shines a little bit like the point-to-multipoint. But what you can use it for is in case you think about coding and erasures, just use the library and it's done. You cannot be worse. There's no use case where it's worse than others. The only thing where I can think about something worse is when you code and there are no losses. And then you don't get a gain, but you have the price of coding. Otherwise, you can always use this form of coding. Okay, thank you very much, and we will see you then next week.